Let us look at these questions of radioactivity and see how we are supposed to respond towards these questions. The diagram below, the diagram in figure 6 shows a radiation emitted by a radioactive sample. So this is the diagram, a radioactive sample. This is the negative and this is the positive. So before even you go to the question, you need to understand if this is the positive, the one which is diffracted towards the negative, you should know which one is it from the characteristics of the radiations N. So M is likely to be alpha. Why? Because alpha is positively charged, therefore it will be diffracted towards the negative. N is beta because it is negatively charged, therefore it is diffracted towards the positive. Another thing you should know is the magnitude of diffraction. Alpha is very light, beta is very light, therefore the diffraction is very big. Look at this one and then look at this one. This is alpha, M is alpha, and the diffraction is very small because it is heavier. This one is lighter. It's lighter. So M is alpha particle. Alpha, we use this sign, and this one is beta particle. Explain what would happen when a sheet of paper is placed in a path of the two radiations. So what will happen? If it's a sheet of paper, then alpha is going to be blocked because alpha, from the characteristics we learned, you should know that beta will penetrate through, will pass through, because beta is only blocked by aluminum sheet. So M will be blocked. Will be blocked or be, yes, while N will pass through. Will pass through the sheet of paper. Yes. Another question. A radioactive substance weighing m kilograms took 1900 years for the original mass to reduce to 15 kg. Given that the half-life of the radioactive substance is 380 years, determine the original mass of the radioactive substance. So we want to calculate the original. I will take you through two methods. So the first one and then the second one. So determine the original. First, you need to understand here. We have, it takes the whole time is 1900 years. But the half-life one is 308. So we want to see how many half-lives are there in these years, the total time, 1900. How many half-lives are there? Because for it to decay from original to a half, that's one half-life. So we want to see, so we want to check number of a half-lives equal to the total time, 19 years, divided by 301 half-life. Yes, this one here once, here it will go 5. So we will have a total of 5 half-lives. So we have the remaining, which is 15 kg. So this is what has remained. 15 kg, yes, 15 kg has remained. Therefore, we want to go to decay, to see the original, where the 15 that was left, where did it come from? So we just have the first half-life. This is the first. So we will do the, now we will multiply 2 because we want the original. If we have the original, we divide by 2, a half. But since we have the remaining, now we multiply 2. So 15 times 2, it is 30 kg. That's first half. Next, second half-life. It is 30 times 2, which is 60 kg. 1, 2, we go to the third one, third, a half-life, 6 times 2 is 120. Fourth, a half-life, because remember we must have the half-lives first, 5 of them, so that is 240 kg. And then the last half-life, the fifth one, it is 480 times 2, it is 240 times 2, which is 480 kg. So it simply means that the original mass was 480 kilograms. So suppose you are given the original mass, what do? We start 480 to 40 up to where we will have 15 kg, the remaining amount. But if now we go half when we have the original, we divide by 2 up to the remaining amount. But when we have the remaining amount, we want the original, and you are using this method, you multiply times 2 times 2 times 2 up to the number of half-lives that you have calculated. I have 5 half-lives, so first, second, third, fourth, 50 half-life. But if that is difficult now, let us use the formula, or we can use this. There is a formula that we use that says that the remaining amount equal to a half times n times original amount, original mass. So we have remaining, it is a half times n. What is n? N is the number of half-lives. Half-lives. N is the number of half-lives. So let us substitute the remaining amount is 15 kg, remaining, reduced to 2, meaning this 15 is remaining, kg, equal to 1 over 2 raised to power n, and our n is 5 years, times original we don't know, we can put y. So use your calculator, 1 over 3 raised to power 5, it is 1 over 32. So that is 15 kg equal to 1 over 32. So 1 over 2 times y is 1 over 2y. We want to remove the denominator times 32 both sides. So kilogram. So 32 times 15 is 480 kg, which is equal to y. So the original mass y equal to 480 kilograms. So you can either use this or this one to get what you want. State 2 uses of radioactivity in medicine. So you will give specifically for medicine, we have for agriculture. So if for number 1, radioactivity is used in sterilization of surgical instruments using the gamma rays radiations. After they have done the surgery, to remove the viruses or the dirty from the instrument they were using, they use the gamma radiations, and those they sterilize them, removing the germs or the nonsense that are there. So number 2, it can also be used to monitor growth in bones and healing fractures. Once somebody has his leg or a bone has been broken, they use the radiations to monitor how the bones are growing and the healing of the fractures. Complete the nuclear reaction below. This is a nuclear reaction. So 226, this is a mass number, atomic number. So it is forming a P with 88, and so you can see that this one is an alpha decay. Why? The atomic number is reduced by 2, mass number has reduced by 4. So 26 minus 4 is 22. Therefore, you complete by writing H, helium 2, 4, and that is all you need. State 2 uses of radioisotopes in healthy, and that's what we have done here. You can give others, we have done that. Distinguish between a neutron and a proton. So what would you say a proton is, and what would you say a neutron is? So let me distinguish that. So a protons are positively charged, while neutrons do not have any charge, and are neutral. So the neutrons are neutral while the protons are positively charged. Both of them are found in the nucleus of an atom. What is meant by a radioactive substance? What is a radioactive substance? A radioactive substance, this is a substance. This is a substance that undergoes radioactivity. In other words, say that a radioactive substance is unstable nuclide or isotope. Unstable isotope is able to undergo radioactivity because it is unstable, therefore it is radioactive. So a radioactive substance is an unstable isotope which is ready to undergo radioactivity. So this is a substance that undergoes radioactivity because it is unstable. 288 grams of a radioactive substance decayed to 9 in 40 days. So the decay from 288 to 9 took 40 days. Determine the half-life of the radioactive substance. So we want to determine one half-life. How long did it take? How many days was it taking to decay for one half-life? So first we have the original and the remaining. So that is simple. 288 grams. So half of 288 grams is 144 grams. Half of 144 is 72 grams. Half of 72 is 36 grams. Half of 36 is 18, and then finally 9 grams. So this is the remaining amount and this is the original amount. So now you can see how many half-lives are there. There are 1, 2, 3, 4, 5. So now we have 5 half-lives. But it takes time from here to decay up to the remaining 9. It takes 40 days. So we know, so if it takes 40 days, so now we have 5 half-lives. So we can say that 5 half-lives takes 40 days. How many, what about 1 half-life? 1 half-life will take how many days? So it is 1 times 40 divided by 5, and this one will give you 8 days. So here it is 80 days, 80 days, 80 days, and 80 days. So 8 times 5, 1, 2, 3, 4, it is 40. Or 8. 1, 2, 3, 4, 5. 80 days, 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 days. So 1 half-life is 80 days. Draw a label diagram to illustrate how alpha, beta, and gamma radiations can be distinguished from each other. You draw a source of, this is a source of radiations. This one is positive and this one is negative. So we know the beta particle is negatively charged. Beta particle is negatively charged. Therefore, it will be deflected towards. Beta particle is negatively charged. Sorry, remember that beta is negatively charged, so it will be deflected towards the positive. alpha is positively charged, it will be deflected towards the negative alpha. Gamma does not have any charge, so it will just go straight, and that is gamma. By so drawing this, you have differentiated them. (100) of a radioactive Pa, atomic number 33, mass number 912, was reduced to 12.5 after 81 days. Determine the half-life of Pa. So we have the final, the remaining amount. We have the days. We have the original amount. That one is very simple actually, because we have the original. So what you do just is just write the halves. From 100 we have 50 grams. From 50 we have 25. Use your calculator if you have a problem in maths. From 25 we have 12.5 grams, and this is the final. They need the remaining amount. So we have how many half-lives? 1, 2, 3. So we have 3 half-lives. This is the first, second, and third. But the entire decay takes 81 days. So they want us to find one half-life. What is the number of days for one half-life? Very simple. So 1, 2, 3. 3 half-lives takes 81 days. What about one half-life? Will take how many days? So it is 1 times 81 divided by 3, and it is 27 what? Days. So 27 plus 27 plus 27 will give you 81, and that is one half-life. Remember, it is 27, 27, 27. Remember that a half-life is a constant. You will not find here 27, here 28, here 29. No, it is a constant. This one decays by a beta emission. What is the mass number and atomic number of the element formed? So we have Pa33 912, which is, now we want to write the nuclear equation. An element is formed which is X. We don't know which element it is, but we know that it is undergoing a beta decay. Right? A beta decay is plus E -1 0, meaning that the mass number will remain the same. So we will have 912. The mass number will remain the same. What about the atomic number? Remember the characteristics. Atomic number will increase by 1. Well, that one it is increasing. Will increase or decrease? That one is the most thing you need to know. Will increase by 1. Atomic number will increase by 1. Remember that. So that now this plus this, it is 33. This one. So what is the atomic number? Atomic number equal 34. Mass number equal to 912. Does not change. M grams of a radioactive isotope decayed to 5 grams in 100 days. The half-life of the isotope is 25. Now we have been given one half-life. We have been told that it takes 100 days. So the complete decay takes 100 days. But one decay from original to half, it takes 25 days. That's half-life. So what is meant by a half-life? What is the meaning of half-life? This is the time taken for a radioactive isotope. For a radioactive isotope to spontaneously decay or disintegrate to half its original amount or mass, original mass. The time taken for a radioactive isotope to spontaneously decay to half its original mass is what is called a half-life. So calculate the initial mass of m of the radioisotope above. So we first get the number of a half-lives because we have that one. The total time taken is 100 days. One half-life takes 25 days. So this one gives us 4 half-lives. 4 half-lives. So if it is 4 half-lives and the remaining is 5, so it is 5 going to 10, going to 20, going to 40, going to 80. So this is 1, 2, 3, 4. There are 4 half-lives, so 1, 2, 3, 4. So the original mass was 80 grams, original mass. You can use the formula also, saying that the remaining amount equal to a half is to power n times k or y or x. Remaining is 5, which is a half times this to power 4 times y. If you raise 4, this one will give you 5 equal to 1 over 16 y times 16 times 16, and y equal to 80 grams original. Explain why it is not safe to store radioactive substances in containers made of aluminium or made from aluminium. Remember, containers made of gamma will stop on repeater, but it will not stop gamma radiation. Therefore, gamma rays would penetrate through aluminium sheets. State 2 factors which determine the stability of an isotope. Stability. So what it determines is the ratio. Actually, the ratio of the neutrons to protons is what it determines, one of the factors. So one factor is the neutron over proton ratio, because remember the stability equal to 1. So that's what one of the factors that depends. If it is less than 1, then the stability is not there. If it is 1, the isotope is stable. Another thing is the total number of the nucleons. The nucleons is the number of protons and the number of neutrons in the nucleus. Therefore, that's another factor in the nucleus. The total number of nucleons in the nucleus also determine the stability of an isotope. So, in other words, you can write here the total number of protons and the neutrons in the nucleus. That is this word stands for. State 2 differences between chemical and nuclear reactions. That one you should know. That chemical reactions are affected by environmental factors such as temperature, but nuclear reactions are not affected by environmental factors such as temperature. They are not. Remember, another thing you should know is that nuclear reactions produces a large amount of heat energy, while chemical reactions produces more amount or less amount of energy. Nuclear, chemical. So you also again remember that nuclear reactions involves protons and neutrons within the nucleus, while chemical involves the electrons in the outermost energy level. So those are the things you need to know. Some two elements are represented as X and Y. Mass atomic number is 8, 13, 16, 27 mass numbers. How many protons does X have? X, how many protons? Protons, remember protons equal to atomic number. So therefore it has 8 protons. X has 8 protons because this is atomic number. How many neutrons does Y have? Neutrons, remember, mass number equal to neutrons plus protons. So if the mass number is 27 equal to neutrons we don't have plus 13 protons. So X equal to 13 minus 27 minus 13, and the number of neutrons is equal to 14. Y grams of a radioactive isotope takes 100 days to decay to 3.5 grams. The half-life of period of the isotope is 20 days. Find the initial mass of the isotope. Find the initial mass of the isotope. So we have the remaining amount is 3.5 grams. We have the total time taking. We have the half-life, one half-life. So one thing we can start, we are sure of, is the number of half-lives. That one is a sure bet here. So which is 120 days divided by 20 days, and it's going to give us 6 half-lives. 6 half-lives. So if the final is the remaining is 3.5 grams, we can now multiply by 2. We multiply by 2, we get 7 times 2, we get 14 grams times 2, we get 28 until we have 6 half-lives. 1, 2, 3. Next is 56 grams. Next is 112 grams. Next is 2, 2, 4. So you just count 1, 2, 3, 4, 5, 6, and it means this is the original. This is where it came from up to here. Remember, when you are decreasing, when you have the original, you decrease by 2 by 2. When you have the remaining, you multiply by 2 by 2 to get the original. So the original is 24 grams, 24 grams. But you can as well use the formula. Remaining amount equal to 1 over 2 raised to power n times original y. Remaining amount is 3.5, which is equal to a half raised to power n. N is the number of half-lives. There are 6 of them. There is 6 times y. So 3.5 equal to 1 over 164. Half raised to power 6 is 1 over 64. Y. We multiply times 64 both sides times 64 so that we can remove this. So it means that y equal to 3.5 times 64, and that one will give you 224 grams. One application of radioactivity in agriculture. It is used in monitoring absorption of phosphate fertilizers. Another one is used in monitoring what? Monitoring photosynthesis. Monitoring photosynthesis and related processes.